All right, let's dive straight into this explainer with a classic exam trap that costs students critical grade boundaries. Right from the start, we're going to look at how a seemingly innocent, totally normal-sounding answer can completely tank your score on the Cambridge 0478 exam.
Imagine you're asked to define the link between hardware and software. You might be tempted to write something like, hardware is the physical parts and software is the apps. Software tells hardware what to do. I mean, it seems logically correct, right? It totally makes sense in an everyday conversation. But here is the harsh reality of Cambridge examiner marking. That answer is going to score you absolutely 0 marks.
So, why does this generic answer get a big fat 0? Well, today we are going to completely destroy this revision myth and replace it with an elite examiner-approved system. You see, that answer fails because it totally lacks computational thinking vocabulary. It doesn't use precise scenario nouns, and honestly, it completely ignores the actual mechanics of how a computer operates under the hood. To get top marks, we can't just state the obvious. We have to show a deep, structural understanding of the exact technical pipeline.
Section 1. Linking hardware and software. To fix that flawed answer, we first need to build the correct theoretical framework from the ground up. Here is your Cambridge Safe definition. It's all about communicating algorithms to fulfill a specific user need. Notice those specific words: algorithms, instructions, and user requirements. Computers put algorithms into action using programming languages. Software isn't just apps. It's a highly structured set of instructions specifically designed to manipulate physical hardware to achieve exactly what the user wants.
Let's map out this 4-step flow. It's basically a top-down journey, from a simple tap on a screen down to the actual physical circuitry. It all starts with the user. That's you. You interact with the application software. That software then talks to the operating system, which acts as this crucial middleman, managing the system's resources. And finally, the operating system sends those signals to the physical hardware. This exact 4-step flow is the backbone of how human interaction translates into machine execution.
Moving on to Section 2, translating code to hardware. But how do those human-readable instructions actually become something a piece of silicon understands?
The absolute crucial point here is this sequence. Software developers write high-level code, translators step in, and machine code is outputted. In its most basic form, computer language is just binary code, literally just a series of zeros and ones. A computer processor cannot natively read Python, Java, or Visual Basic. No way. It only understands on and off electrical signals. That means the high-level programming languages that we humans use must pass through a specialized piece of software called a translator to become that binary machine code.
Now, what's really fascinating is comparing the two main types of translators, compilers and interpreters. A compiler takes the entire high-level program and translates the whole shebang all at once into machine code before it runs. This makes the final execution incredibly fast, but it can be a real headache to spot errors if the program crashes. An interpreter, on the other hand, translates and executes the code line by line. This is brilliant for debugging because it stops the exact moment it hits an error, but it does make the overall execution slower. Understanding this trade-off is a very frequent requirement in exam questions.
Now, in just a second, I'm going to give you the hidden examiner clue required for full marks regarding sudden system events. But first, think about this. Normal sequential translation is fine when everything goes perfectly. But real-world computer systems are chaotic. Things crash, users click randomly, hardware glitches out. So what happens when the system needs immediate attention?
That brings us to Section 3, Interrupts, Hardware versus Software. Let's explore the mechanics of how a system handles these sudden requests.
An interrupt literally pauses the current CPU process to handle something way more urgent. Think of it like this. You're reading a really good book and your phone rings. You put a bookmark on the page, answer the call, and then go back to exactly where you left off. That is precisely what the operating system does. It receives an interrupt signal, pauses the current software process, deals with the new urgent request, and then resumes its normal operations.
You have absolutely got to memorize this contrast for the exam. They will frequently ask you to categorize or define the two types of interrupts. Software interrupts are usually signals sent by applications that hit an internal issue, like a mathematical error, say division by 0, or two processes trying to grab the exact same memory location. Hardware interrupts, though, are physical triggers from the outside world, like pressing a key on your keyboard or clicking your mouse. Both demand the operating system's immediate attention, but they originate from completely different places in our pipeline.
Section 4, Inside the CPU, Registers and Logic.
Once that data or interrupt reaches the hardware, where exactly does the central processing unit store and process it?
Before data is processed, it must flow into one of these 5 specific temporary data storage areas called registers. We've got the program counter, the memory address register, the current instruction register, the memory data register, and the accumulator. Each of these has a highly specific job in fetching, decoding, and executing the machine code we talked about earlier. Remember, the CPU is just processing numerical digits in their most basic binary form, and these registers are the actual physical hardware storage locations holding that data mid-calculation.
All right, let's test your logic with a quick checkpoint. Imagine a security light that turns on if it's after 6 p.m., we'll call that input A, or if it is dark outside, which we'll call input B. This is a classic inclusive OR logic gate scenario, so pause and predict. Under what exact conditions will that light absolutely stay off?
Looking at the 4 possible states of this system, the only time the output X is 0 is when both inputs A and B are strictly 0. If it's after 6 p.m., the output is 1, so the light is on. If it's dark, the output is 1, so the light is on. If it is both after 6 p.m. and dark, the output is still 1. The only way the light stays off, an output of 0, is if it is not after 6 p.m. and it is not dark. This perfectly illustrates how high-level software logic translates directly into binary hardware circuitry.
Section 5. Upgrading to top marks. Now let's close that curiosity loop from earlier and apply this entire framework to upgrade our 0-mark answer from the very beginning of this explainer.
Let's look at the fix. We are throwing out that generic software tells hardware what to do nonsense. Instead, a top-end answer looks like this. The user interacts with application software, which communicates instructions to the operating system. The operating system then uses a translator to convert high-level algorithms into binary machine code that the physical CPU registers can execute. Do you see the difference there? We apply the scenario nouns and use the exact technical terms: algorithms, translator, machine code, and CPU registers. That is how you secure full marks.
And here is an elite exam strategy rule you should always remember. Generic repetition is the enemy of top band scores. If a question is worth 4 marks, you literally cannot just rephrase software controls hardware 4 different ways. You need 4 distinct technical points. You might mention the role of the OS, the translation to binary, the use of logic gates, or the storage in registers.
To make sure you master every single command word and framework just like we did today, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCS. We'll help you absolutely excel in your Cambridge examinations.
Now that you have the system to upgrade your answers and stop losing those easy grade boundaries, your mandatory next step is to watch our 7-day revision map explainer. You urgently need to schedule these exact techniques before exam day. Having the knowledge is really only half the battle. Knowing exactly when and how to review it in that final week is what guarantees the highest grades.
We've seen today how beautifully, how logically, hardware and software communicate. But I want to leave you with this thought. What happens when a malicious actor uses this exact same hardware-software pipeline to inject a software interrupt or overload your CPU registers on purpose? Think about that vulnerability, apply today's framework to it, and I'll see you in the next explainer.